So I first met Larry in 1984 when I was visiting Cambridge, and I can still remember bits and pieces of advice that he gave me that I've carried around with me every day. So he's really gentle, sweet, generous person with his advice, and his work has just been he's been a force of nature, I'd say. He's Russell and Whitehead rolled into one. So, I'm looking forward to hearing Larry's talk on proof assistance from symbolic logic to real mathematics.
Thank you very much, Shankar. What I'm going to try to do today is say something to both the mathematicians here and maybe also people here who are already experts on proof assistance and don't need to be told what they are. So for the latter, those of us who know about proof assistance are probably very much in the mindset of our particular one, which we know to be the best one. So I'll be reminding us, as I am trying to tell mathematicians what proof assistants are and the various dimensions of them, will help us, the rest of us, remember what these design choices are. So first, what do we mean by formalized mathematics? Well, first of all, computers and mathematical proof have been somehow starting to get intertwined for a while. So there's the famous proof of the four-color theorem, the original 1976 one, and of course Tom Hales has talked about the Kepler conjecture. Another one I might want to mention, the Robbins conjecture being confirmed in 1996 using special software he'd written himself for that very purpose. Now, one thing these all have in common is that mathematicians hate them. They have two reasons for hating them. One is that they are dependent on a big pile of code, and why should anyone trust all this code? And a second reason, certainly in the case of the first two proofs, you would want a thing like the Kepler conjecture to be true for a good reason, right? You've got all these spheres, they're packed in this beautiful symmetric way, and that is using the maximum volume. And you would like it to be true because it's got to be true, and therefore a proof that involves checking thousands of cases somehow seems wrong, but that's just the way the cookie crumbles, as people say. So, as for the third proof, it turns out that proof was simple enough that somebody was able to take the original proof found by the computer software, write it up as a normal journal article and publish it in the Journal of Algebra, and suddenly it was an okay proof, you see. So if it's appeared in a normal journal, there's no problem. But we're interested in the other cases. Now, how about a question?
Yeah, it's a comment. I object a little bit to this notion that Bill McCune wrote a special software. I mean, the Robbins conjecture was obtained by EQP. EQP was a theorem prover for any equational theory, possibly with associative commutative function symbols. So it was not something built only for the Robbins conjecture. It was a theorem prover.
My impression is he coded EQP with the objective of proving the Robbins conjecture. So, and there's maybe a bit of ambiguity. It was a general purpose theorem prover, as you say. But certainly he had the motivation, at least, of building a thing that would prove the Robbins conjecture.
Yes, it was a motivation, but that is different from saying that it was ad hoc software.
Okay.
I mean, you could have given to EQP any other equational conjecture as long as it was in an equational theory. I mean, I used it also for other problems, so it was not only for Robbins.
Okay. Oh, yes. I understand. Anyway, and thank you for that. Now, as for proof assistance in mathematics generally, well, in particular, we saw those other two cases suddenly checked in proof assistance, and people were a lot happier. Now, why exactly? Well, first of all, the one part of the proof that people don't like, that is the case analysis, which meant it wasn't true for a single good reason. We couldn't get rid of that, although I gather the number of cases has gone way down. In the case of the four-color theorem, no doubt George knows exactly the number of cases being checked was greatly reduced by improved proof.
Yes, but not by me.
Still quite a few cases to check. But of course, they are now not just a whole bunch of code that somebody wrote, but now they are running in, well, still a whole bunch of code, but very specialized code that has been checked and rechecked by many people, and the whole point of it is to provide a verification environment. So surely the level of confidence is way, way up, although, of course, no one can ever say definitely that anything is true. And also the complicated arguments in these things, the mathematical arguments, were also verified in a formal deductive system. So our confidence in these goes way up compared with before. Now the question, I think really the question of this whole workshop and this whole program is, are we really ready to, are proof assistants really ready now to use for mathematical research, real mathematical research? And I want to begin, as a reminder, I know there are many people here who aren't familiar with proof assistants, to review the history of them. Well, a selective history from my memory, sorry. And I think the earliest thing I'm going to mention at least is the Boyer-Moore theorem prover, a very influential system which actually survives to this day in ACL2. Verifying, in the beginning, it was very much about verifying code, so proving properties of simple functions written in Lisp, so little properties of lists and natural numbers, which by the end of the 70s they had verified the the prime factorization theorem, which by the standards of its time was seen as a great development. I know that for mathematicians it's trivial, but you know, there's a lot of technical complexity even in getting to that. Another highly influential system, the LCF, was interested in verifying code again, verifying functional programs written in a peculiar domain theory devised by Dana Scott. Then there were this one totally forgotten thing made by Mike Gordon for verifying hardware. So you had like networks of things inspired by CCS. Finally, the HOL system, which has been mentioned a lot today, direct descendant of LCF, so there's still lots of code shared between all these systems. Oh, I've done something wrong. I must have switched it off. Sorry, it's on again. Lego, and I see the builder, Randy Pollock is here, yes, there's Lego. And if you say, why didn't I mention Coq? Well, I'll be talking about Coq quite a lot anyway, and Coq and Lego, I mean, these are from the past, and Coq is still in the present. Now that version of HOL is also in the past. There is, of course, Automath, which is very important. These are very important. Why are these a different color? That's because these are the only systems that were designed in the first place to do mathematics. So all the others were designed to verify computer code. There's a difference in intent there, and therefore there's a difference in design and a difference in like everything. So both of these in particular, Automath and Mizar, could be argued as being really based on a foundation of mathematics. Mizar being based on a classical set theory, and Automath suddenly introducing this propositionless types idea out of nothing, and really very, very, very much ahead of its time. I mean, you were doing Automath on computer punch cards and putting a deck of cards through and getting a very obscure type checking error out. Okay, and finally, yes, all of the formalisms were weird. Certainly, I would imagine that any mathematician would look at almost all of these formal systems. Maybe Mizar, being classical set theories, is the least weird, but many of them would look very unnatural, I'm guessing. Okay, so that's a bit of history. Now, what I'm trying to point out is that we as computer scientists started with the objective of verifying code and verifying systems, and suddenly found ourselves doing mathematics, doing non-trivial mathematics. And it came out of fairly obvious things. So if someone says, I want to verify a floating point algorithm, and if you think of what that involves, I've got a particular algorithm for the log function. It might be a very short sequence of instructions. I suddenly need a model of an exact, precise model of floating point arithmetic, let's say 64-bit IEEE compliant, whatever. You've got to specify these floating point operations. Of course, you have your algorithm. You suddenly need to have a mathematical theory of the function that you are verifying, and prove. You need a specification of what it means for it to be correct, which means I believe that the difference between the true logarithm and the logarithm that you have calculated has got to be 2 to the minus however many bits in your mantissa. So a very precise, a very technical thing which you need to prove, and obviously a lot of mathematics goes into doing that. And of course this will be an extremely tedious proof, and if you ask why you're doing this tedious proof, I'm not going to show you a picture of anything blowing up, but it's about, this was all inspired by the division bug in the Intel Pentium chip that cost Intel, was it $500 million? Anyone know? Yeah. So the idea that a very insignificant, because like the actual magnitude of the error was very small, but even so they felt they had to recall the chip. So these things really have to be verified, and suddenly an enormous amount. Now this is very trivial math, you might say. It's only a bit of real analysis, but that was the starting point. Then, and I'm sorry, this is a very selective history, Joe Hurd came along and said, can we verify a probabilistic algorithm, like the probabilistic primality test being the most famous example? I know several others. And it's interesting because you might think at first, how could there be a verification of something probabilistic? But he set up a rather cool framework using measure theory, I think, where you could actually talk about all possible futures or something like that, and showing that indeed the probability of getting the wrong answer complied with the advertised properties of the algorithm. But then you suddenly needed Lebesgue integration and probability theory to be formalized by machine. And to mention some more recent work, Sylvia Boldo, whose work on numerical analysis, and suddenly you're needing a lot more. Again, maybe to a mathematician this is still a trivially small amount of mathematics, but it's certainly much more. Remember, you see, these systems started from pure logic, and by the end of the 1980s, we still had not even negative numbers, right? So going from negative numbers to partial differentiation, we can at least say we've been making progress. Okay, now at some point along here, people started wanting to verify mathematics for its own sake. Now there is some pushback against this. It's like, well, it's a waste of time. Everything, but you know, not everything needs to be pragmatic. And one of the nicest things, and of course Jacques is here somewhere, revisiting Isaac Newton's proofs of Principia Mathematica and trying to actually do his infinitesimal proof calculus by using non-standard analysis. So that's a quite beautiful, I mean, you could argue it's a historical thing to think Newton's proofs, which did not use calculus in the normal sense, but instead used infinitesimals, were nevertheless sound, and they were sound enough that we could even identify places where Newton actually made mistakes. That's interesting, at least historically. And other people started kind of seeing it as a challenge. So Jeremy, who's also here somewhere, doing an elementary proof of the prime number theorem, and John Harrison, who is not here, doing the prime number theorem in Hall-Light. Now John didn't want to do an elementary proof. He instead wanted to formalize a vast amount of complex analysis. And some of this stuff, things about winding numbers, which are trivial to mathematicians, turned into several hundred, no, probably a couple of thousand lines of totally unintelligible Hall-Light proofs. And this is actually a problem we are still up against. Of course, there's the odd order theorem, which is this enormous development done in Koch by Gonthier and his team, and Assia over there. So, and which of course stands as the landmark at the moment for machine formalization. And just to mention some things that I did because I'm standing here, so some work on Gödel that I formalized in Isabelle. So people are doing these. Why? Well, one reason is simply if there's a doubt over the proof. So I mentioned the four-color theorem. There were doubts about the proof using a computer program. Again, with the Kepler conjecture, exactly, and Tom gave very eloquently how after 4 years they still hadn't even started refereeing the paper because they didn't know what to do with the code. That was kind of depressing. And in fact, the reason I verified Gödel's incompleteness theorem, I was sitting right here in the Newton Institute several years ago, and a logician, I don't know his name, he said, why don't you verify Gödel's second incompleteness theorem, because no one has really written it down properly, or something of that sort, which I thought was a fairly extreme statement, but anyway, here we are. Also, it's useful sometimes we see things that are not quite in the statement of the theorem. These are typically very small hidden assumptions, but sometimes the exact definition of the scope of the theorem is not clear. Now, a thing that some of us are interested in, and indeed was mentioned this morning, the idea of codifying mathematical knowledge, the idea that a codex of maths would be valuable in its own right. But certainly the main reason I'm going to push is about errors. Now, I don't want to go here and say mathematicians make a lot of mistakes, but I was very happy to discover about this particular page, which is page 118 of this book here. I may even have a PDF copy of one way or another. So this is on that page. The author noticed there are a lot of things that didn't quite work. So you see, it's kind of sad. And it's not only these maybe very obscure mathematicians. It'll be online later, I'm sure. This one, because now we're talking about David Hilbert, so not just a bunch of maybe second-rate mathematicians who made a lot of mistakes, but David Hilbert. Now, this is unbelievable that Hilbert's work needed to be corrected, and Olga Tauski worked for 3 years to fix the errors. So this is an issue. Okay, so let's say we have decided we're going to formalize mathematics and we're going to use some kind of machine. We have to make some decisions. And what I thought I would talk about today are these 4 things here. I'll go into more detail. There are, of course, many, many more choices we have to make, but these are choices that have, shall we say, different choices have been made by different systems represented here. Obviously, I represent one system which I believe made all the best choices. But I do have to also reveal all the wrong turns that people could make. So one could ask, should we use some kind of type theory or some sort of set theory? Now, an interesting thing, actually, and this is a real question, what exists out there? So in the 19th century, certainly there was a lot of people, not everybody, but a lot of people who believed that there was a real notion of set, and it was a big problem when Russell's paradox came along, because before that it was assumed that if you could think of a concept and it was precise, then the set of all of the things existed. And then Russell showed that that idea led almost immediately to a contradiction. So that meant we needed a more subtle notion of set, and we eventually arrived from the set theory world with the cumulative hierarchy and the whole axiomatic set theory thing, which is now very well understood, and which I guess most people are willing to say is a perfectly okay way of doing mathematics. Now, I also had the great privilege of meeting De Bruijn when I was an undergraduate at Caltech, and De Bruijn was one of the few who thought intrinsically that set theory was wrong and it's not evil, maybe even evil. And for him, so we mostly say if you got a line is a set of points. Whereas for him, no, a line is a line, a point is a point can be incident on a line, but they are different things. So I think this is a personal attitude. Now, obviously, De Bruyne was a very great mathematician, and if that's how he felt, no one can reject that and say that he was wrong. How could one do that? And other mathematicians will say, aligned with a set of points, and I'm happy with that, and you can't really say they are wrong either. So this is something that lives in our heads. Nevertheless, if you're building a system, you have to make a decision. If you use type theory, one thing you can do is use a simple type theory, this going back to church, and having many, many different forms. We have our higher order logic system, so they have some polymorphism, which gives us some flexibility. We can even have type classes, which gives us even more flexibility, and I'll talk about that a little bit because that's the world I live in. Or you can go in a different direction and have a thing called predicate subtypes, which gives you a different kind of flexibility. Of course, Shankar is here to represent that point of view. Then you can have these richer type theories represented, and I think the first great example, of course, is automath, and De Bruyne showed very elegantly, and when I say elegantly, I have to say the actual notation of automath is totally barbaric, and yet I remember De Bruyne introducing it, and somehow to me it was beautiful, and wow, he's introducing this axiom. It's a primitive notion, this builds on it, that builds on that, and it just, there is a beauty to it, even though it is at the same time appalling. And of course, he formalized a lot of stuff in automath. And then, of course, we have more modern things like Koch, Agda, and I'm sure there are others in which tremendous works have been done. And yes, so De Bruyne, as I said, who created automath, and in his mind, those types were the things that existed, whereas sets were not. Okay. But then if you live in the set theory world, or you like the set theory world, you're fine with that. You don't mind the idea that the sine function might actually be the exact same item as, say, some number you're interested in. Now, probably they're not equal, but of course, set theory being a completely untyped world, it is potentially the case that any one object you're looking at, like some real number somewhere, might be the very same object as some triangle you might be talking about. And if you're a set theorist, you really don't care. And the two systems I know that implement classical set theory are Mizar and Isabelle ZF, although I know of there's someone here who has built another implementation of set theory in Isabelle, which is an amazing piece of work. So one could take any of these as starting points. And by the way, as Mizar is not so well known, it's worth mentioning that Mizar has an incredible system of soft types which allows them to combine, shall we say, modifiers on things, so that if you talk about a field, it could be a finite field, and I don't know a lot about fields, but a finite whatever field, and make theorems in which you're combining these properties in a very natural way, so that they're able to express a lot of mathematical concepts. Because Mizar, unlike most of these systems, was designed by mathematicians, so it does all these things very well. And it's an example of what you can do with classical set theory, in fact. Now, in case you're wondering what is Isabelle ZF, that is the result of me formalizing a set theory textbook. And the problem with that, set theory textbooks are in principle about mathematics, but in reality, they are only about set theory. So Isabelle ZF is really quite good. If you want to formalize a theorem that you found in a set theory book, it will be great. But if you want to do even a very elementary fact about mathematics in general, it's probably not very good at all. Okay, now I want to say a little bit about type class polymorphism because we use it a lot in Isabelle, and it's a quite powerful compromise. Because whatever we're doing in a formal system, you have to make a lot of compromises between the power of your formalism and the amount of work the system does for you. So by type class polymorphism, I mean we're working with simple types, we don't have dependent types, but we do still have the ability to axiomatically define a lot of abstract things and actually combine these, so it's a bit like the adjectives, the modifiers in Mizar, they're not as flexible. Combine them together, And then we can have a kind of hierarchical proof in which we do a lot of proofs about these properties in a general sense, and then and also with a notation for these things in a general sense. So in the abstract setting, we can prove an awful lot of things. So we can prove a lot of things about, let's say, topological spaces or Euclidean spaces or partial ordering. So we can prove lots of maybe very, very difficult proofs about Euclidean spaces. And then, oh sorry, I want to go back a bit. But then once I know that a particular thing is a Euclidean space, which I prove once and for all, suddenly all the stuff we know about Euclidean spaces becomes available to that construction, whatever it was. Now I have to say that the dependent type system will be more flexible than this. A set theory system will also be more flexible than this. But they impose their other costs, of course. Anyway, let me keep going. Another one of the dimensions on which our systems differ is the issue of things being defined. So if I write x divided by y, we are making the assumption probably that that thing is meaningful. But if you're in a formal system, you then have to decide what exactly is going on here. The approach taken in, let's say, a lot of our classical type theory systems is to say that everything is defined, but sometimes what you get is not very interesting. So the don't care approach then, we don't know what 1 over 0 is. Could be anything, well, it has to be a number because we have a type system, but we don't know which number, but we definitely know that this number is equal to itself because reflexivity always holds. So this is one approach, and of course people will defend it, other people will criticize it. But another way of dealing with this is to have some kind of way of doing what a mathematician does. So somehow, if you want to write x divided by y, you need to prove that y is non-zero. So, and I'll probably be slightly wrong about Coq, but I'm still in Coq. Probably you have in the type the evidence that y is non-zero that has to be supplied. Is it still like that?
Depends on which library.
Depends on which library. Now I know for certain in AutoMath you definitely, division actually takes 3 arguments. It takes x, the y, and the third argument is proof that y is non-zero. So that's definitely how it worked in AutoMath. Now PVS works differently again, where you put in all your specifications, and then I guess it goes through some kind of checker, which then spits out a list of things you have to prove, and one of the things that you ask you to prove is that y is non-zero. So that looks a lot cleaner. One of the problems with the don't care approach is that you cannot have a notation like derivative of this or integral of that, because they may not exist. So we typically find yourself working with a relation that is x is the integral of y, or x is the derivative of y, and then that relation tells you that the thing exists and stands in that relationship. And finally, there's an approach which people have pushed a lot, but not with much success, shall we say, the free logic approach, where now we talk explicitly about definedness. Now, of course, a mathematical text does this all the time. They say, we have now proved that the integral exists. And that's quite normal mathematical discourse. Doing that in a formal system is not so easy. So in particular, then, this thing now becomes false because typically in a free logic, if you have an atomic formula and it has undefined things in it, then it is false. It's slightly awkward because then I believe the negation of it will be true, which somehow doesn't quite seem right. But also you find that you have to prove everything is defined everywhere, and that gets kind of tedious. Okay. Now another dimension of difference is how do we actually express our proofs? The first thing I need to say is that without some kind of automation, it's hopeless. And I recently, what am I doing? I recently saw a paper by Adrian Matthias in which he pointed out that the definition of, I think it was the number 1 in Bourbaki's formal system, if fully expanded, went to, I think it was more than 1 trillion signs. So you need We need definitions, but even with our definitions, we still need automation. But the question is, what sort of automation? Now, the one approach you can take is to use decision procedures. The great thing about decision procedures is they have a very clear domain of application. So if my problem fits, if it is a linear arithmetic problem, then it will be definitely solved by linear arithmetic. And I know then that it's totally predictable and it will definitely solve the problem. On the other hand, we have, let's say, lots of naive stuff, like saying, if I see x plus 0, I'm just going to throw that 0 away. Shall we say a common sense approach. These both have their good and their bad side. The bad side of decision procedures is that the thing you want to prove always has one extra thing in it which is outside the decision procedure, which kills the whole thing. The bad side of the heuristic approach is that somebody is always coming along and saying, I would like to cancel out something else, that should cancel, and then suddenly 25 other proofs fail because they had worked before, but now you're changing the way the heuristics work. So how do we cope with this? Well, and of course, actually in Isabelle we use both, but it's a thing we have to live with. Actually, I will mention a bit later ways that we can cope with the heuristic proof-breaking problem. But at the moment, I want to present you with more of the difficulties we are facing. Now, mathematical notation is one of the real killers, actually. Now, people love their notations, but honestly, how can you defend, okay, that's function application, that's an image, simply because it's an uppercase variable, it's suddenly an image, that's an inverse image, that's a product, that's applying the inverse, and so is that, but that is squaring the whole expression. That's a product, and that's probably a different kind of product, but I'm not sure. And of course, that's a...
You cancel the D's.
No, you can't. You might want to cancel the D's, but probably it's not a good idea. But the machine notations are awful, so I can understand people would like to preserve these, but there is a vast amount of ambiguity in these. So let's look at a machine. So this is HOL light. That's what HOL... Actually, this is nicer than some. So the number 0 in HOL light as a complex number is horrible because you have to take 0, you write a 0, then it has to be coerced to a real number, so you put an and sign in front, and that's the real 0. And then you have to put another thing in front to convert it to a complex number. So it is Cx of ampersand of 0 is the number 0 as a complex number in HOL light, and that's pretty brutal. This is not so bad, although we see here that, what is this? That's meant to be 0 and that's meant to be 1, but they are not elements of R, the set of reals, but the set R to the 1, which is the set of one-element vectors of reals. And you say, why in heaven's name are you making a distinction between real numbers and one-element vectors of real numbers? Well, let's just say that's a HOL light thing. And it would be hard for me, it would be rather technical to get into the reason for that. So you see, you get into an awful tangle very quickly. Remember, HOL light is one of the best systems for doing mathematics. So you see what we're up against. And one of my really big objections to this sort of proof is that you cannot see any intuition at all in all of that. It's just, all we have is system says it's true. And I don't like that. So one of the things I've been doing, and yeah, this is a little proof, right? One of these can be 2,000 lines long. I have been porting a lot of these myself, so I ported this. This is the same proof in Isabelle. It's still not beautiful, but I would like to say it's at least quite a bit better. The notation is slightly nice. We can write really 0 and 1, so we don't have to use that vec thing. And what you can also see is that we are showing some intermediate things. So where you see the word show, that's something I'm trying to prove. You might not understand all the notation, but you can see I'm trying to prove this thing, I'm trying to prove that thing, and I'm proving that thing under those assumptions. So we have a proof with some structure and with a lot of signposts inside telling us what we're trying to prove. So this proof structuring, which by the way Macarius, wherever he is, put so much work into, this structured language, this by the way is totally ripped off from Mizar, so if you're a Mizar person you can feel gratified. In fact, it's called Izar, right? So even in the name, Izar, Mizar, you see the homage is there because, you see, Mizar was designed as well to make legible proofs for mathematicians, and so we have the same idea here. And I would argue that we really need legible structured proofs, partly because maintenance. So I mentioned earlier, if you like heuristics like I do, and you don't like your proofs breaking because you've changed your heuristics, what you need is these structured proofs with lots of little local scopes so that when it breaks in a very identifiable place where you say, it was trying to prove that thing and it broke right there, and okay, all the rest of the proof is fine because it's structured and the hierarchy said all those things are fine. This one little thing needs to be fixed. But also, this sort of proof where you have a legible structure, you can hope to say, I understand how that proves, and I'm going to take this part and I'm going to use it for a thing I'm proving tomorrow. And maybe one day we will be able to translate these bodies of formal mathematics into some more advanced system. So let's maybe in 5 years say Lean, for example, will be really mature and terrific, and has a more general language. It might be then possible to automatically translate these enormous libraries into Lean. Now you say, what evidence do I have that these things could be translated automatically? And the answer I would give is that I translated about 50,000 lines of HOL manually from HOL to Isabelle without understanding. 95% of the time I had no idea what on earth was being proved, what the statement of the theorem said, or what on earth, why these things were about these homotopic paths or whatever. God knows. But somehow the proofs came out. You see, so if I could do it with so little knowledge, I think a computer could do it as well. But also, and I know that many mathematicians will be skeptical of trusting a lot of code, and I think having a proof that you can read helps add to the confidence in our systems. So I have this text exchange here. You see, why should I trust your system? You talk about your architecture. We have a small kernel. Well, your kernel is 1,000. Actually, 1,000 lines is kind of small. The Isabelle kernel is quite a bit bigger. I think HOL has 1,000 line kernel. But here, that's 1,000 lines. Why should I trust your 1,000 lines? Okay, well, we've done a proof. We've verified the whole kernel. But what they see, what a skeptic will see, is just 10,000 lines of code verifying the 1,000 lines of code. So you're just getting, things are getting worse and worse, so you see you're getting very fed up at that stage. Whereas we could move to a new paradigm. Now he says, why should I trust your system? Don't trust it. Okay, you don't want to trust it, don't trust it. Just read the proof itself. And now he suddenly realizes that everything we're doing is like, that's trivial. And that's trivial. That's trivial too. And then we have to admit that our systems do not have the minds of real mathematicians, and the steps that they do really are very small. And so then our mathematicians say, yeah, trivial, right? So then you can still, but at least they believe us, right? So that's what I would like to move to.
Larry,
Yes?
don't we have that already? Mathematics textbooks and papers? Don't they have legible proofs in them?
More or less, but they're not also formal. We want to be formal and legible.
Arguing that it's reliability that you're improving.
Well, we have both. We have both. We have legible proofs, but they are also formal and machine checked at the same time. See, the textbooks, and actually the textbooks are not always that legible either. But anyway, so now the question is, are we really ready? Now, actually, I would say, well, sort of, well, are they sound? I think they're, and people will always argue about soundness, but I think we have a pretty good correctness record. I wouldn't argue for a perfect one, but a pretty good, and when people do find flaws in our systems, we're generally able to fix them reasonably quickly. Certainly, anything that has gone through one of these tools has been scrutinized to a way further level than something that has been written down just on paper. Automation is getting a lot better. And now people in these various systems, they've got a very sophisticated logical reasoning, Grosvenor basis stuff, more and more sophisticated decision procedures all the time. So our automation is improving. And certainly we have some very, very big proofs in all the main systems. They have, and this is hard, like when I was doing this in the 80s, you know, a computer with 8 megabytes, that was really big. And you know, you think, well, could this really scale to a specification that was 3 pages long? I think that's a really big specification. Well, somehow everything has got way bigger and we have coped. So, I mean, that is good. And all of us have been, again, and as Tom Held mentioned this morning, that foundationally higher order logic is really quite limited. Not having things like ordinals and cardinals. Nevertheless, you can do a very large chunk of mathematics, even in these very limited systems. So we can do a lot. Our libraries are getting better. So there's this, the famous mathematical components library that was used for the odd order theorem. And then there's a separate one used by Sylvia Boldo, also in Koch, with a lot of real analysis in it. There is the immense HOL library. I think it's not only John Harrison, but other people. And stuff is pouring into this at the rate of, was it 100 theorems a month? I believe, yes, 100 theorems a month going into the HOL source. Is really kind of scary. And I don't know if that is just John Harrison or other contributors. And of course, Isabelle's archive of formal proofs, that's probably already outdated, because stuff keeps coming into that as well. So we have libraries. So in a sense, we have a lot of good things, but I'm afraid the story is not only good. First, I want to briefly mention, maybe this is kind of pointless now. So the idea about needing nearly 400 pages to prove 1 + 1 = 2 really doesn't apply to us anymore. So maybe that's not a problem. What about Gödel? The main thing to remember about Gödel is that he showed the limitations of any one formal system, but as long as you don't insist on having a universal formal system, we can forget about this. And of course, what we're trying to do with undecidable, but in general, but we are not trying to replace human beings, we're merely trying to assist human beings. So those are not real problems. What are the real problems? Is that although we have libraries with millions of lines in them, we still don't have the whole of undergraduate maths or anything close to it. So a mathematician comes along and says, I wonder, where's your theory of bounded variation? We don't have one. You don't what? You know. So that's not very good. Our proofs, and even though I was claiming that we had legible proofs, I'm sure a lot of mathematicians would say they don't look very legible to me. And you don't link to any source. I don't know where you got that from. So this is a problem. And also, and I've heard a lot of people talking about this, even this morning, how do I find out what there is? And especially when things are formalized in weird ways. So, and finally, and maybe the killer, is that automation is still very, very limited. I was just, excuse me if I use the board for a moment, puzzling recently about how do I prove a theorem which says, suppose I've got a line and some points are on the line, and this is a connected set of points, which clearly means it is like that. Then I need to prove that this is a convex set, and our convex set is one which, if you draw any 2 points, they're connected. So this is a completely trivial theorem, completely trivial. And yet one has to think, oh, I can make a mapping from here to here and do this and show it's injective and show blah, 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 blah. And then finally, after like 30 or 40 lines that I've struggled over for hours, I established this completely trivial result. So this is a big problem, and I think that anyone who wants to use this will need to be very patient. Never mind, we are working hard. What could we do? What could help people now? I think, for example, natural language search right now, like a Siri for formalized mathematics. So what is in your system about bounded variation? And have it come out, I'm sorry, sir, there's absolutely nothing. Or, or whatever. Then we have the following 17 theorems. That would be useful. So similarity-based search. So are there any existing proofs that look a bit like the one I'm in the middle of now? So yes, there was something else that had exactly the same assumptions, a compact set in a Euclidean space with a continuous function, blah, blah, blah. That maybe could be done now. And then it could say, why don't you, maybe you could insert this in your proof because this was what the guy did in the other proof. Maybe some codified textbooks, so the idea that you have a very important text which people need to learn, and you could have it formalized in such a way that you have the formal text linked to the informal text, so kind of answering Tobias perhaps there, that you have both the readable human text and you have the formal equivalent, and there's somehow a linked document. And the thing I think others have mentioned, computer algebra systems are used a lot, but they are still not completely trustworthy, and it would be nice to have completely verified things available within our systems. So what do? We need to make our libraries bigger, so we still need contributions. We will, I'm sure that the undergraduate curriculum should be within reach within a few years, actually. I would really like to do some work on the actual mining of libraries for reusable components. Of course, we need to keep working, and we need to keep talking with mathematicians. So that is the end. Thank you.
That was a most agreeable talk.
Thank you.
Very nice.
Yeah. So Arnold.
So I'm a mathematician.
Okay.
I want to raise something. The three statement and the conclusion.
Okay.
So Koch believes in a proof only if you speak its language. Isabelle believes in a proof only if you speak in its language. I believe in a proof only if it speaks my language. So the real problem in working with mathematicians, in getting mathematicians to accept it, is that the systems must speak their language and not just any formal language.
Well, there's been some work on getting systems to communicate, and the usual approach, which I don't like, is to find a lowest common denominator, so to take the Isabelle or the Koch and compile it down to some extremely low-level thing, which is somehow fed into the other system, which somehow digests it and then says this is a theorem. What I would like to aim for instead is the kind of thing I was hinting at, where I show a structured proof where you can read the structure and imagine that structure somehow being copied into another system that also recognizes proofs that have some structure in them, and somehow in the new system either rediscovering or somehow transferring the argument used in the other one, so that you have copied the proof at a high level, inheriting all the structure of the proof. So as for you, I mean, in the sense of your notation as you write it on paper or something, I do think there's too much ambiguity in there for us. Certainly, I don't know at all how one would cope with that, but at least the idea is that if you can see it in these two different systems with the structure of the arguments there, that there would be something you could internalize and understand for yourself.
So, but would
You're
this be
not
a
very
deal
happy.
breaker for you, that you couldn't write it in your own notation? Would it be a deal breaker?
Well, I'm interested in this stuff, otherwise I wouldn't be here. And I spent an enormous amount of time in reading things, and I was always unsatisfied. And I have many ideas of how to bridge this, and it's a real necessity, because this is the real thing that keeps mathematicians from trying to use this stuff. If you need a month to get familiar with a strange language, and then if you need 10 or 50 times as much time to writing something in this language, which you write very quickly in your own language, nobody is doing this, except if you really need it because of getting your work accepted in the community.
Well, I'm not claiming we're ready yet. Is Andy the next one?
Do you have a response?
I would just say I don't think, I could not honestly say that our tools are ready yet. I think I'm speaking to those of us doing research that we are trying to make them ready, but I would not claim they are ready right now. So I'm agreeing with you in a sense. Andy?
And there's a different approach, right? Not work with mathematicians, but you just wait for those ones to die. When you grow new ones, what I'm thinking is if you wind back 50 years, no mathematician worth his salt would have typeset his own paper. He would have had his secretary do it, right? But these days we typeset our own papers and we don't think twice about it. So just grow new generations of mathematicians who are just used to using these systems. You're not going to ever succeed with the existing mathematicians. We're just too old. We're too set in our way.
They won't be used to doing this.
I have a different suggestion that, when a mathematician retires, they're forced to formalize ghosts of proof.
Yes.
No, there is a real issue. And I said with that example there, which I puzzled about for a couple of days, because it's trivial. So there are still, there are real problems. Not even about notation. It's,
I know that that's true.
what? No. Anyway.
State your name and...
Yes, exactly. Text. I'm a programmer. Writing readable code is a skill that programmers have to learn in order to continue being employable. I'm wondering, your examples of structured proofs are still not the proof objects themselves, right? Why should we not instead program our proofs, write the programs so that the theorem provers we use would have the De Bruijn criterion, and so the proof objects themselves will be directly visible instead of being manipulated by means of an indirect imperative program which does not have to do with the actual proof.
Well, I would say two things. First, there are no proof objects in Isabelle or HOL. And the reason there aren't is that Robin Milner discovered in 1975 that his computer didn't have enough memory to store proof objects. And even though it is now 2017, and we have a lot more memory than we had then, but our proofs are also very, very much larger. And now if we switch on the proof object option in Isabelle, we find that it still runs out of memory. So we don't want proof objects, number one. But number two, we don't want to look at them because they are extremely large in size. I don't think they're necessarily a trillion signs for the number one, but they're extremely large, and they don't convey any intuition about the proof.
And on the other hand, I think you might like Agda, for instance.
Indeed, I do. If I might, what you're talking about is equivalent to the assembly code, and indeed, programmers don't necessarily read the generated assembly code. However, they write in a higher level programming language, like Agda.
Frank and then Bas, yeah.
Okay. I really like your talk, but you're the Isabelle person, right?
Yeah.
So you're going to aim for these goals. What are you going to add to Isabelle apart from growing more libraries? I mean,
almost any system is going to want to grow their library. I'm sure Coq is still growing their libraries, and Hall Light for sure.
But what are you going to do yourself to change the world for the better in this respect?
How I would like to change, well, I know that I have some funding, hoping to hire some actual mathematicians and have them do some of these things. So in particular, one of the real things I want to do is this mining of libraries. So the idea that you've got like 2 million lines of existing proofs, seeing if you could find recurrent patterns and connect these recurrent patterns because they're structured proofs so that we can see the actual arguments. And if we can connect them with the particular facts available in the current user's context at this moment. They've got a compact set, they've got a continuous function, therefore they could do the following thing, you know, the inverse image is also a compact set or whatever, and that they might want to do that and have it maybe suggested for them, or if they ask for help, have it suggested. That's one of the examples. So using these libraries to help build and help grow the libraries even more.
Bas Bitter, Orange University.
Mm-hmm.
You were comparing the type class approach in Isabelle with the one in dependent type theory, and you said the latter has issues. So could you compare the type classes in Isabelle with that of, say, Corlin?
I didn't want to say the latter had issues, because to be quite honest, I don't know a lot about type classes in dependent types. So I wouldn't want to say anything. And indeed, I know, of course, the whole odd order proof was done using type classes in Coq, and it's clearly an immense achievement. So I could hardly say it has issues, but I don't really know a lot about it.
Okay.
Anyone else? So Larry, say something controversial.
Maybe I have already, but Michael, does there time for
Yeah,
Michael over there?
I always think if we want to help mathematicians, and you had it on your slide, we should assist mathematicians, not replace them.
Absolutely.
And one of the things, just looking at practice, is that mathematicians tend to be extremely good at proofs. Okay? They're even mainly correct in their proofs. And the thing where mathematicians have trouble is finding the result they need for becoming unstuck on a proof. Finding that somebody has done the same stuff already under the name of Jordan C-star triples without being aware of it. And those kind of things that are much more horizontal than the kind of vertical art of which is very, very focused in finding proofs. I know I shouldn't say this in a big proofs workshop, but I'm wondering whether this whole aspect of verification and so on isn't barking up the wrong tree. And I see the big advantages that we're reaping out of big proofs are kind of the secondary Teflon pans, where we're re-examining the math and trying to, and actually succeeding in making it better, and so on. And so, shouldn't we keep building tools for those aspects rather than looking at proofs, which may be at the level, at the wrong level anyway?
Well, you'd be talking to the wrong person, because I do these proof tools, and that's what I do. And now there is, for example, the field of mathematical knowledge management, which sounds much closer to the kinds of goals you're talking about, and they do what they do. But in fact, the things you mentioned, like finding out whether there's already a proof of what you're trying to do, or looking for a thing that would help you finish a proof that you're in the middle of, is exactly what I would like to do, only within the context of the system I'm using, right? Because the idea, indeed, it would be terrific if one could have the more broader goal, like I'm working in Isabelle, I want to know, is there a proof of this lemma in Isabelle? No, but there's a nice elementary proof of that appeared in the American whatever, 3 years ago. You could formalize that. That would be terrific. I think that's more than I could do myself, but I totally agree with you. That would be a terrific thing to have. Is there time? Yeah.
Oh, well, you said be controversial. Yeah, so my contribution to be controversial is, we all do it, I do it too. We talk about the mathematicians as though they are one big blob. Actually, there are a huge variety of mathematicians with different skills, different competencies, doing different things, all the way from proving Fermat's theorem to the Met Office to whatever. And it's somehow, well, it's certainly a little bit patronizing, just as it would be if, on the other side, the mathematicians kept on referring to all of us, or many of us, as the computer scientists, or them, or,
Or even worse, the IT experts.
So it's almost as if, one way to shift the conversation is to shift the language and think a little more broadly about how we talk about the community we're trying to engage with.
Yes, thanks.
So that actually, raises the question of, broadening the audience. Maybe, could we make things so usable that school children could mess around with them? Even philosophers could.
Well, I think if you mean school level, like calculus problems, I think there are tools like this thing called Math Expert or whatever, which I think can already do that sort of thing. Yeah.
But yeah, I think it's usability is also
But they don't do a lot of
because
proof
we
in
would,
school.
stand a lot of pain to use these things because we have a stake in that. But a customer might be less willing to put up with the pain.
For sure.
Okay, so if there's nothing else, let's take a break for 30 minutes and come back here at 4 o'clock
Stephen Watt.
to listen to Stephen Watt's talk.
Very good. Very nice.